So welcome back. Last week we started Module 7 and we'll be continuing that this week, as well as getting into Module 8 a little bit, which is going to be strings. Keep in mind that after we come back from the break, we will have our midterm on that Wednesday. So we'll have a review the week prior to that, but remember that don't forget everything over that 2-day break, because right when you come back, that's when the midterm is. So keep that in mind, keep that in the back of your mind as we go forward over the next couple of weeks. To remind you of what we did on Wednesday with regards to arrays, I'm going to hold a little mini review here as well as a visualization of this stuff. So remember that arrays are basically collections of elements that can be accessed using zero indexing. If you've got an array of size 5, those elements are going to be indexed at index 0, 1, 2, 3, and 4, right? If you've got, so the last one is not at index 5 because you don't start at 1, you start at 0. If you've got an array of size n in general, the last one is going to be at n minus 1. There are two ways of building up arrays. One is using static arrays, and the other is using dynamic arrays. And as I demonstrated to you on Wednesday, using static arrays, it's okay if they're very small, but if they're even moderately large, several thousand, even several hundred elements, basically you are abusing the stack space. Remember that the program's a stack. You've got a stack frame upon stack frame upon stack frame each time you call a function. Well, what happens if you stack too many dishes? It all eventually falls over. What happens when you put on too many stack frames? What happens? We call that stack overflow, right? And so you've got to be careful. It cannot hold very many things. Is there a question over there?
You say the static arrays are allocated on the heap.
Static arrays are allocated. Oops, sorry. Yep, thank you. On the stack. There, thank you. And thus are limited. And we saw that in action when I tried to create an array of, say, 1 million elements or whatever it was, 2 million elements. Your stack is limited to several megabytes, or if it's an embedded system, you're limited to maybe a few K, right, or a few hundred K, and you cannot abuse the stack space. So to solve that problem, we introduced dynamic arrays, which are allocated on the heap. The heap is a lot less organized area, but it's a lot, and efficiency, that's a different question, but it's also a lot larger. And we did successfully allocate enough space for millions upon millions of integers upon the heap. To do that, we used a function called Malloc, which is short for memory allocation. And remember the way that we use this. We simply asked Malloc to give us a chunk of memory of a certain size. I could ask Malloc to give me a chunk of memory of 1,000 bytes. However I intend to use that 1,000 bytes, that's my business. Malloc doesn't care. It just says, here's your pointer. It returns a generic void pointer that simply points to a memory location. If you want to treat that memory location as 1,000 divided by 250 integers, that's your business. If you want to treat that memory location like 1,000 divided by 8, doesn't go in evenly, I don't think. I'd have to do the math in my head, and I can't do that right now. But if you want to treat them as doubles, that's your business, right? So to solve that problem, we used a macro called Sizeof. So that instead of asking for a raw number of bytes, I want 1,000 bytes or I want 2,000 bytes. Instead, you ask for as many bytes as an integer takes or as many bytes as a double takes times as many that you want. All right? So let me go over to our first demonstration here. And this demonstrates the difference between a static array and a dynamic array. I'll go ahead and increase the size here. So I've got an integer n here. I'm just going to create an array of size 5 and fill it with values 10, 20, 30, 40, and 50. A is statically allocated, meaning that over here in the stack, the main function right here, it takes all of those local variables, including n, which was declared right here, b, which is a pointer variable, and a, which is an entire array that holds 5 elements. This is allocated on the stack. This is small enough that it's going to be okay. In general, you don't want to do this, though, because you're abusing the stack space to do it. You're basically declaring 5 variables, even though it's only one variable, it's in an array. You're putting all of those variables on the stack. So let's walk through this a little bit, right, and see how it changes. I'll decrease the size a little bit so that we can zoom up there. So we initialize n to 5. Then I use Malloc here. I'm asking for n integers, because that's n up here, 5 integers times size of int. Size of int just simply says, well, an integer takes 4 bytes on this system. This way, if you take the same code and you port it over to another system on which integers only take 2 bytes or 3 bytes or something like that, you don't have to change your actual code. Size of int will return 2 or 3 in those cases instead. So you don't have to hard code the values. It makes your code interoperable, portable to other systems. Okay? So we've asked Malloc for n times however many bytes an integer takes so that it'll allocate enough space for it. And then what we're doing with that generic void pointer that it returns is that we're forcing it to become an integer pointer. So that this generic void pointer that's pointing to some memory location, we're going to make it, we're going to say, okay, well now it's pointing to a memory location that holds integers. If our intention was to create an array of doubles, we'd cast it as a double star, right? Int star on the left-hand side matches int star on the right-hand side. I'm making them compatible with each other. Let's go ahead and go forward now, and you can see that B is a pointer now that points to a memory location that's been allocated on the heap, right? Which is much larger, less well organized, right? A heap of stuff is just a pile of stuff, and you throw something on top, it may end up somewhere. But a stack is much more organized, but it's smaller. So there's a trade-off here. Okay. Let's go ahead and keep going forward here. I'm just simply going to fast forward now. All I'm doing is allocating 10, or I'm initializing 10, 20, 30, 40, 50. Right? And let me go back to the first part here and tell me what values are in, by default, what values are in either one of those arrays? What does it indicate right here with the visualization? A question mark. Who knows? Right? There could be garbage in there. We don't know. There could be whatever was stored in there before you actually called the, started using that. Right? Whatever was left by the old program or your program. Remember, there are no default values for any of this stuff. And because there's no default values, it's being visualized here as a question mark. On Wednesday, when I went through and I printed out a bunch of values, we saw a bunch of random values, whatever happened to be stored there originally. Okay? So if you need default values, you need to go through and set those default values because they're not going to be set for you. There is another cousin to Malloc called Calloc. C-A-L-L-O-C. Operates a little bit differently, but it does initialize everything to the null bytes, in other words, everything to 0. Right? If you want to use it, go ahead, RTM, read the documentation, right? Or read the manual. So now you see the difference between a stack and a heap allocation. One is static, and in general you should not use it. One is dynamic, and that's generally what you want to use. Okay? So with that, remember memory management. Once you've created something, you have to make sure that you clean up after yourself. Once you've created something, once you've created dynamic memory, you filled it with a bunch of values, you process those values, now you're done using it. You need to clean up after yourself. If I just fast forward here, right, all the way to the end, then eventually my program is going to die at this point. It's done operating, and this memory, all of the memory will be cleaned up for me by the operating system. But if my program were to go on and continue operating and do a bunch of other stuff, then I would lose this memory right here. Right? It would leak out is what we called it. It's a memory leak. Now to show you this, what I'm going to do is I'm going to edit this code a little bit. What I'm going to do is, okay, I'm done with that array. I'm going to create a new array. B is equal to, and I'm just going to say this stuff. Right? I'll allocate a brand new array for this stuff, and then I'll go through and set it equal to, oops, cancel that. Didn't want to save. I'll go with 100. I'll go fill it with 100, 200, 300, 400, and 500. Okay? Now let's visualize this execution and see what happens here. Give it a second. Okay? And I'm going to go ahead and fast forward here until it gets down to that point. So 50. There we go. All right. So there's B pointing to that thing. When I execute this next line, let me zoom out so that we can see it on operation here. What's going to happen? This pointer is pointing to that memory location over there. On line 16, when I change this pointer to point to that brand new memory location over there with newly allocated memory, what happens to that old memory? I've lost my pointer to it because I changed this pointer and I'm pointing over here now. So does it get cleaned up automatically? Nope. It leaks out. All my values are still stored there, but I have no pointer pointing to it anymore. I have no way of cleaning it up, freeing it up, and that memory is no longer available to my program. When the program dies and the operating system goes in and cleans up after it, all that memory is reclaimed. It's not like I'm deleting memory or anything because that's not possible, but it's gone and unavailable for my program. Right? Let me go ahead and see what the visualization does. Do you see that? Right? It disappeared, in fact, up here. And this is brand new memory over here. When I go through this loop, now 100, 200, 300, 400, 500, right? The old memory location, it was leaked out. I wish the visualization would show this memory leak. Right? But memory leaks are notoriously difficult to find. But there are tools to do it. You'll examine one such tool tomorrow in lab. We give you a program with an intentional memory leak. You'll try to suss that out and look at it and see, oh, okay, well, there's the memory leak. There's where I need to clean up after myself. And if you, oftentimes you miss stuff like that. And so there is a tool, I forget what the tool is called, not Memstat, but something else. It's in the lab tomorrow. But you'll run it, and it'll actually analyze the memory usage and say, oh, you lost you lost this memory over here. You lost this memory over here. You lost it there about here in your code, so you may want to take a look at that and see how you should go through and do some memory management, clean up after yourself. Right? So there are ways of detecting and addressing this kind of stuff. But if your program was long running, like say a browser or a full application like Microsoft Word or something like that, and your program was running for hours and hours and hours, allocating memory and not deallocating it, freeing it up, well, then you would eventually run out of memory and your program would either die or your entire system would grind to a halt. Right? So you do need to be careful about that. That's memory management. Make sure that you free it up. So let me go ahead and edit this code again. What should I have done here before I reallocated this to point somewhere else? Before I take this pointer and make it point over there to that memory location, what should I do to that memory? I should free it up. Remember that is free B. Then you can make B point to somewhere else. Once I've freed that memory over there, it's gone. Right? It no longer belongs to me technically. Trying to free it again, that's double free. Trying to access those values, trying to do anything with those values is undefined behavior. You might get away with it, but hopefully you don't get away with it. So hopefully it would detect that and do a segmentation fault. But since it's your memory, you're just screwing up your own program. Right? And that's the operating system doesn't care about that. All right, I'll go ahead and copy paste this so that you can have it in the notes when I update them later. All right. So now that we've discussed, why is that not? All right, fine. Now that we've had a little mini review here, let's start talking about how to use arrays with functions. So using arrays with functions. Right? Remember, when passing an array to a function, you need to do your own bookkeeping. I don't know if there are two. Yeah, I don't think there are two Ks there. Bookkeeping. What does that mean? Here's an array. I've created an array. Is there any reliable way of telling how big that was? That there were 5 elements in there? That there were 10 elements in there? No. What do you need to do? You need to keep track of the size of an array in another variable, just like I did up here. Int n is equal to 5. That ends up being the size of my array. So that when I allocate it, I remember there were 5 elements in there. When I iterate over it, I remember that there were 5 elements in there. So in other words, if I'm going to pass an array to a function, I need to do my own bookkeeping. You also need to pass in the size of the array. Using a separate variable. Now what kind of variable should that be? Should that be a double variable? Can an array be of size 3.5 elements? No. It should be an integer, right? And you can do bounds checking on that integer. Can you have an array of size -10? Doesn't make any sense. You can have an array in most instances of size 0. Here's a memory location of size 0. There's nothing there. You can do that technically. But generally, if it's negative, then yeah, you want to be able to do error, you want to do error handling on that kind of thing. Right? So to pass an array to a function, you pass a pointer, right? And of course, as we just discussed, and the size of the array. Right? So for example, because an array's identifier, that is name, is already a pointer, when you pass an array, you only pass the name of the array. Right? So let's take a look at an example. My example, I'm going to write a function that takes an array and sums its elements. Okay? And I could go into code mode here. Let's see what it looks like. Okay. It's sensible now. So what should I call this function? So here's an array of 10 elements, whatever they might be. Go through and add them all up and tell me the total. What am I doing? Total, I could write total. Total, however, is a noun, right? Do I want to generally name functions nouns? Functions do things. Functions are verbs. So what verb were you using when you add things up? You could call it add things up, but sum, all right? I'll call it sum. So of course we could add documentation to this. Again, generally documentation is added to the header file with the prototypes, and you separate them all out. Since I'm just writing these for notes, though, I'll go ahead and keep them together. This function takes on. Now, what are we adding up? We're taking. We could take an integer array, add that up. We could take a double array and add that up if you want to instead. We could take a character array. Does it make sense to add the characters C plus the character H plus the character R, my name, right? You could do that, but you would just be getting the sum of all the ASCII values, which may be what you want, but that's not what I want here. So let's just go ahead and limit this to an integer array. This function takes an integer array of size n and returns the sum of its elements. Okay. That sounds good for now. So what's the return type going to be on this function? The sum of a bunch of integers is what? Is an integer, so we'll return an integer. Now what does it take as inputs? I need a pointer to the actual array. I'll just call it ARR because I don't know what this array is representing. Is it representing NUIDs? Is it representing drops of rain? Is it representing seats? Right? I don't know. So it's just generic. It's just a generic integer array. So I'll say that it's ARR. Is that all I need? What else do I need here? I need the size of the array. And I already said that in the documentation here it's of size n. So I'll pass that in, n. Right? Now this should be pretty straightforward. Here I will call it total. Int total, right? For int I equals 0, I is less than n, I plus plus. That's so idiomatic there that you'll just want to do that pretty much. Anytime that you are iterating over an array, you're going to have a loop that looks something like this. Okay? And then I'll say total is equal to total plus array sub I, the ith element in the array. Right? And then at the end, I'll return total. Right? Now, there's one improvement that we can make here. There are a couple of improvements that we'll make here. And there's one error in the code that I just wrote. Can you tell what the error is going to be? Yeah. What's in total as of line 210 right there? Again, there are no default values in C. So it could be garbage. It could be 0. It could be dead beef. It could be -5, right? -5 plus whatever's in my array, is that going to be correct? No. Dead beef plus stuff is not going to be the stuff that I want. So I need to initialize this variable here. Okay? That was the one error. What's one improvement? How could I improve this and elide it to make it a little bit shorter? Plus equals. Right? Great. That'll work. Let me take that over, and let's open up REPL and do it in REPL here, because I don't want to visualize it. All right, there we go. I'll go ahead and create an array of an array of elements here, int primes. Right? So here's let me zoom in so that we can see it. Get rid of this. So let's go ahead and create the first n primes. Remember that you can use this this syntax to initialize, create and initialize at the same time. 2, 3, 7. Oops, 5. 7. What are the other primes? 13, 17, 19. All right, that's good enough. 23. Right? How many primes was that? If I call this function int total is equal to sum of primes, what do I pass in as the size of this thing? Well, you can count them up, but also a compiler can count them up. But if I'm going to be passing this off to a function, I need to be doing my own bookkeeping. Is there any way, like you might have seen other programming languages, like say Java, where you can do something like this, primes.length, or primes.size, or maybe there's some function out there that you can call size of primes, right? None of those things work. And you might see some terrible, terrible advice on Stack Overflow even, saying that you can do this. There are some instances, particularly static arrays, where you can determine the size. But that's only because the compiler is saving you from yourself. There is no reliable way to get the size of an array once you've created it. Right? So what do I need to be doing? I need to be doing my own bookkeeping. Int n is equal to whatever the size of this thing is. How many primes did I write? 4, 5, 6, 7, 8, 9. Okay, so there are 9 of them there. Okay, I'll pass in n as a command, as a argument to this, and then I'll print out the total. Total of the first %d primes is %d. I'll go ahead and print out n, and I'll print out total. So, do you know what the, did anybody do the math real quick to check us to see if this is right? All right, fine. I'll have Wolfram Alpha do it for us. Sum of first 9 primes. 100, wow. So, we should expect 100. Hey, great, we did it. All right, well, what if I passed in a value, say 4 instead? Is that going to work? Yeah, why not? It's just going to iterate over the first 4 of them. The first 4 of them exist. So let's run this again. Well, we can ask Wolfram Alpha again, but hopefully everybody would be able to do that in their head. 17, right? So let's run this and see what it looks like. Yeah. Would I be able to pass in 50? What's going to happen? Hopefully a segmentation fault. It's going to go beyond my array. It's going to go out of the scope of my array because I said that this array is of size 50 when it's only of size 9. Right? I lied to the function. Well, if you lie to your functions, then there's nothing that they can do about it. Right? It's just going to continue iterating over this, probably give you either some wrong value. It could end up in a segmentation fault. Let's find out what happens here. Some of the first 9 primes, or the first n primes here, the 50 primes, is some negative value. What happened there? Obviously, it summed up the first 9 of them. Then it started to go into memory locations that belonged to me because I didn't get a segmentation fault. I was only screwing up my own memory. I was only reading my own memory. But it was getting a bunch of garbage values, deadbeat values that have no meaning. Right? And that was the result. It's just some value, some number there. Probably repeatable too. Nope. Some random value. Whatever was loaded up there in the program to begin with. Whatever garbage happened to be in that memory location when my program started. Okay? That's why I'm getting random values every single time I run this. Because random garbage is in there each time. Okay? So make sure that you're doing your own bookkeeping and that you're not lying to your own functions. Okay, yeah.
Can you make a for loop that counts for you? Let's say you have a set of data, you know the number, you want to count them out alone.
Nope. How do you know when to stop? Right? How do you know the difference between this is my memory that belongs to that array over there, and then whatever's coming after that, that's something else. Maybe in memory, if the memory doesn't belong to you, the operating system hopefully detects that and kills your program with the seg fault. But if it's memory that belongs to you, yeah, you can keep going all you want, right? It's not going to stop you. Right? So no, there's no reliable way to determine the size of an array if you're not doing your own bookkeeping. Yeah?
You are able to define an array without having to define each value separately immediately, right?
Correct. But what's in there? Question mark. Dead beef, zeros, depends. Right? All right. Well, there's still an improvement that we can make on this thing. Okay? What if, in addition to summing them all up, I went ahead and made them all, I changed them all. I changed them all to -1. Right? Would you expect this function to do that to you? You gave here's your nice array that you created, full of primes, right? And you gave this off to an array, and you just said, please sum this up for me. Do you also expect it to erase all your data? Probably not. If you ask a bank teller, oh, give me my balance. Okay, I'll give you your balance, but I'll also zero it out. No. And so what we're going to do then is we're going to prevent this, right? And I'll show you that this actually works. Let me go ahead and copy this up here and paste. And instead of changing it, we're going to go ahead and use printf, %d, comma, arr sub I. And I'll show you that indeed all of them have now been changed to -1. Or it's not called array here, it's called primes. There we go. And we'll run this, and we'll get the correct total again because we fixed that error. But now it's -1, -1, -1, -1. Right? I changed the data. Right? I don't want to do this. Right? If I give my data off to some function, I don't want it making changes without my permission. So what we can do is we can prevent changes to this. We can make this into a const array. Const is short for, what do you think? Constant. Now, it's not a constant as in, like, it can never be changed. But in the context of this function, I'm going to give you an array, and you're making you're the sum function now. You're making the promise that I'm not going to change anything. I'm going to treat it as a constant. Like, you can't change pi once it's been created. You can't change e, right? You can't change false. It's always going to be 0 or whatever, right? By putting a constant in front of it, now you can see what's going on here. There's a big red line under this now. What does that mean? It's a compiler error now. The compiler is seeing, oh, wait, you made the promise that you're not going to be making any changes to this array. You violated your promise down here on this line. So compiler error, you need to resolve this. Are you going to take away your promise and allow it? Yeah, okay, it could make changes, maybe, maybe not, who knows, right? You're taking a gamble there. You're throwing the die. Or you make your promise, and the compiler will enforce that promise for you. Right? Now, there are ways around this promise. It's not an absolute promise, but you have to pretty much go out of your way to violate and break this promise. It's not a promise in the sense that it gives you a guarantee that it's not going to change. It's advertising the fact that, look, I'm not going to change it on you. Okay, you go ahead and use this function with the assurance that I'm not going to change this on you. Of course, you could always be underhanded and lie to them, right, and violate your own promise some other way. I'm not going to show you how to do it. It's fairly easy, but you can see the result here. That by making this promise, then the compiler is at least able to check rudimentary that you're not violating this promise, right? So const no longer allows this, right? And so I'll get rid of that, and now I'm assured that it's not making changes, and you can see that they were not all changed to -1. It retained the data. So if you're not going to be making changes to an array, then go ahead and design it so that const is there, and you're advertising the fact that you're not making changes to the array. Okay? I'll go ahead and put that up here in our final design of this function. So const it gives a promise that no changes will be made to the elements in the array. Right? In general, be conservative. If you are not going to be making changes, design your functions to use const. Right? Now, this is only an issue that's just come up just now. Why weren't we bringing up this issue before when we first talked about functions? For example, n. What if I change that to 50 here? Or yeah, let's go 50. Right? Could I put a const in front of that? Well, I could. I think that it'll enforce that. But we never covered that. Why? How is n being passed? Remember, there's one of two ways that an element can be passed to a function. By reference or by value. Right? Which one is this one for n? By value. Meaning that the value n, of 9 here is being copied onto the stack and passed in to this function. So is it possible at all for this function to change this n over here? No, because all it ever gets is a copy of the value. So there's no reason to worry about whether or not a function is going to be making changes to values that I pass by value, variables that I pass by value, because it's not possible at all. If it wants to change it, go ahead. You're changing your copy of the variable. You're not changing my copy of the variable down here. Of course, this would totally screw it up, right? And you get, again, those mysterious random values from before because it's going beyond the memory location that it should be. But that's on the function, right? That's the function's fault, not my fault, right? That's the library designer's fault, okay? All right. So, another observation. When we pass in an array, say primes, we are passing a pointer. In other words, a reference, a memory location. Right? When inside the function, using the square brackets, dereferences automatically for us. Right? In other words, generally when we had a pointer before, the way that we would assign a value or look at the value would be to dereference it and then add it. Right? We could do something like this: dereference it and then add it to the total here. But what does this actually do right here? So array is pointing to a memory location. Let me go ahead and bring up. Yeah, I've got some. Yeah, there we go. I've got some paper here. Let me switch over to the .cam. All right, as it's starting up. Remember that our array is a pointer, right? It's pointing somewhere. There we go. ARR. Now, when we first started looking at pointers, focus, we talked about pointers as if it were only ever pointing to one thing, right? And it can point to a memory location that only contains one value, 42. But as we've seen now, we can actually have a pointer that points to an entire array. It points to, say, 5 of them instead. Right? Well, what is this memory address? This memory address is actually pointing to the first memory location. Right? And if we dereference it and get ARR, let me go ahead and fill this with values 10, 20, 30, 40, and 50. When we dereference it, what are we actually referring to here? We're referring to this element, and then we're referring to that value. Right? In other words, 10. Right? It's only if you treat it like there's only one thing, then there will only be one thing. Right? What is ARR sub 0 doing? It's basically the same thing, but it's syntactic sugar, basically. That, all right, dereference it and go 0 memory location, 0 bytes away from it. So dereference it, go to this memory location, and then jump 0 bytes over. Well, I'm not jumping 0 bytes is staying where you are. So in other words, you're getting the value 10. What about ARR sub 1? That's dereferencing it like this, jumping to this memory location, and then jumping 1 cell over to this memory location, which contains 20. Right? Well, how did it do that math? It just did it automatically. Because it knows that this is an integer array, and that each one of these is 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes. Right? So it knows that this memory location plus 4 bytes gives me this element right here. ARR sub 2 means that I'm going to this memory location, and then 2 times however many bytes it takes, 4 bytes, 8 bytes. I'm going to jump over 8 bytes to give you this element over here. And this is how memory actually works, in C at least. That this indexing scheme here is actually a way of doing what's called pointer arithmetic. That you're going to a certain memory location, and then you're going to an offset. Okay? So when you do something like ARR sub I, right, this is equivalent to a dereference plus an offset. The dereference, again, is just a memory location. The offset, I, is times the number of bytes an element takes. All right? So I times the number of bytes. If it's an integer, then it's going to be 4 bytes. If it's double, then it's going to be 8 bytes. If it's something else that takes 3 bytes, then it's going to be 3 bytes. I times 3, right? And what we do is we add these together. And this jumps. This is called random access. It jumps to the appropriate memory location. All right? It's really convenient, because if you didn't have this, then you'd have to do your own pointer arithmetic. And to illustrate that, let me give you an example. What if I wanted ARR sub, say, 5, right? And this is an integer array, okay? I want to go to the, is this the 5th element, by the way? No, it's the 6th element because you start at 0. Equivalently, what I would have to do here is I would have to dereference, and then I would have to add 5 times however many bytes an integer takes. Remind me, how many bytes does an integer take? 4 usually, but do I want to write code like that? Size of int. Right? Now, which one is more conveniently written? Dereference and then add, or just use this? Right? This one wins out as far as brevity and clarity. Right? Now, you'll see code out there that does stuff like this. In fact, in some cases, it's necessary if, for example, you have a generic void pointer. And we'll look at those cases later on. You can design functions that take any type of array. It can take an integer array. It can take a double array. It can take a character array. It can take an array of user-defined structures, right? And if you pass it a pointer, not only do you have to tell it how many elements are in that array, but you also have to tell it how many bytes each element takes, because it's going to need to do this pointer arithmetic manually instead of doing something like this. Right? So now you understand why we start at 0. Because if you want to dereference and get the first element, how many bytes over do you jump? None. 0 times size of integer array. And that's why we start at 0 instead of doing the human thing of starting at 1. Okay? All right. So let's go back. There we go. All right. And that visualization is in one of the videos too, a little bit better than I could do over here. Yeah?
Is there a simple way to access the memory address of a particular part of the array? Since it's
Yep. You could here 5 integers. If you really wanted to jump between them, you could. You could access each individual byte, and then once you've got a byte, you could access each individual bit if you want to do doing something called bit masking, but that's not something we're going to cover.
What if you needed the memory address of something stored in there? Because it's automatically dereferenced.
Oh, you could use an ampersand there, yeah.
Oh, okay.
What he means is something like this. Could you get a memory address of the third element? So here's ARR sub 3, right? Or that's not the third element. What's the third element? 2, right? And so how do I get the memory address of that thing? Well, if this is just a regular old variable, right, because I've dereferenced it already using the indexing scheme, put an ampersand in front of it. And now you've got the memory location of the third element in that array if you really wanted to do something like that. And you will want to do something like that when we do string manipulation, but probably not with integers. Okay? You'll note that I'm not talking about arrays of characters yet, because those are called strings, and that's the next module. Right? We're only dealing with integers and doubles so far. So yes, you can do it. Whether or not it's universally useful, that's another story. Okay? Okay. You can also return arrays from functions. Right? You can write functions that return arrays. How do you return an array? Well, what is an array? How do you represent an array? An array is a chunk of memory. But my pointer is how I refer to that array. ARR is int star ARR. It's always pointing to the first element in that array. So if I'm going to create an array and return it, what type do I need to return? Can I return it an int? One int? Nope. What do I need to return? An integer pointer, right? To return an array, you simply return a pointer to a pointer, right? In general, you cannot and certainly should not return a static array. Never return a static array. And we'll talk about why here in a second. So as an example, design a function that creates an array of a particular size and fills it with ones, returning the resulting array. There we go. Okay? So very simple. Let's go. I'll forego the documentation here. Since we've got it up there, you just cut and paste and rewrite it if you want to. Let me go ahead. What should I call this thing? So here's a trick. Remember that functions usually should have variable names, right? I could call it ones array, right? And that would make sense. Anytime you find yourself using a noun, though, for a function, think, well, what could I do to make this into an integer? Or not an integer. What could I do to make this into a verb? I could put get in front of it. And unfortunately, it's a lot of code is riddled with this. Get this, get that, get. Just to have a consistent naming convention of having a verb as a function name. So you get ones array. Okay? That's what I'll call it. So help me out here. What should it take as input? You want a ones array? What's the next question I should ask? How big? Right? Int n. Right? Now, it's not taking an array as input because I'm the ones array now, right? Why would you give me an array to fill with ones when you're asking me to create it for you? Right? So I'm not taking that as input. Instead, that's going to be my output, int star. I'm returning a pointer. So here's my first attempt. Int ARR sub n, and then for int I equals 0, I is less than n, I plus plus. Again, an idiomatic for loop to iterate over an array. By the way, why am I using a for loop? Why not a while loop? Because I know the size up front. I know a priori, up front, how many iterations I'm going to go through. So a for loop is a lot more natural. And I'll fill it out with ones. And then I'll return ARR. Okay? Now, don't worry about the underlines here. This is not a compiler. Let's take it over to REPL and see what it has to say about this. All right? Do you see a compiler error here? Not an error. You do see something down here. This is just a warning. Address of stack memory associated with local variable ARR is returned. Okay? What I want to do is I want to take this over to our visualization tool here and Let's get rid of this stuff here. Oops. And n, that's good enough. B, there we go. And instead of creating it myself, I'll go ahead and call get ones array. And I want it of size 5. Okay? Let's see what this looks like. Hopefully no warnings here, and it will actually lets me do this. Excellent. All right. It's letting me shoot myself in the foot. Again, it just asked me for what caliber I wanted. So forward, forward. Now I'm going to go into this function. Right? We're inside this function. We create an array of size 5. Where is it? Is it over here on the heap? Unfortunately, it's not even visualizing it at all. But is it over here on the heap? No. Where is it? It's over here on the stack. Right? And unfortunately, it's not even visualizing it here. To get it to actually visualize, I'd probably have to hard code this to 5. But we can do that really quick. Edit this code. All right. Just for the purposes of visualization, I'm going to hard code that to 5. But you don't do that in general. And, well, in fact, you don't do this at all in general. Because take a look at where it actually allocates this thing. Where is it allocated? So I'll fill it up with ones, blah, 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 blah. There we go. Where is it located? In the program stack, because it's a static array. Static arrays are allocated on the stack. I'm about to return to the calling function. What is going to happen to this stack frame, get ones array stack frame? It comes off the top of the stack. What did we call that? We push things on, we pop them off. What's going to happen to that stack frame? Destroyed, right? And wow, I really like that visualization. What does B have now? You can't see that? What is that thing? It's a poop emoji, right? Why is it doing that? Because it's now dead memory, right? When you pop a stack frame off the top of the stack, there is no guarantee on what gets filled in there. In fact, some programs will zero out the stack just in case that there was sensitive data there, so that it can't be accessed once that the stack frame has been destroyed. Return values could be rewritten. Metadata could be rewritten to that memory location. You have no guarantees on what's located there anymore. And in fact, I really like this. Just poops there now, right? You can't access. It's just garbage now, right? So you can't return static arrays. Instead, what do you need to do? You need to create a dynamic array using Malloc. Right? Now, how big of an array do you want here? In fact, let's go back over here and fix this. Edit this code. All right. Star ARR is equal to Malloc. Oops. Int star Malloc. How big of an array do you want? N? What does that do when n is 5? It gives me 5 bytes. How many integers can I hold with 5 bytes? 1 and a quarter. Right? It doesn't make any sense. I need 5 times the number of bytes that an integer takes. Right? And now I can return this dynamic pointer here. Let's go ahead and visualize this execution. And you'll see that that stack frame is still destroyed, but the actual memory is not. Forward, 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 right? And this initializes over on the heap. So that when I initialize everything, blah, 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 ones array, when I end up returning, this thing is destroyed over here. This get ones array frame is destroyed, but the heap memory is not. The heap memory is still there because I have a pointer to it. B is now pointing to it. Now, if I lost that pointer, right, it's called a dangling pointer, then yeah, I would have a memory leak. Right? But you cannot return static arrays. Instead, you need to return dynamic arrays. N times size of int. Okay? So hopefully that visualization, resonated with you. All right? All right, one last thing. Actually, no. Let's do this part first. So shallow versus deep copies. Okay? So as another example or exercise here, write a function to create a copy of an array. Right? So we're going to write this function, but first I want to show you what happens when you don't do it correctly. And this is my second visualization over here. Okay? Now let's look at this program really quick before I start walking through it. On line 6, I create a variable called n and set it equal to 5. On line 7, I create a new array called a of size 5 integers. And I go through and I assign it values 10, 20, 30, 40, and 50. Okay? Let's go ahead and walk forward and see that visualization. Okay? There. A is now pointing to this array over here, and it's full of 10, 20, 30, 40, and 50. Now, what's going to happen on line 12? There we go. I create another pointer, and I set it equal to a. If this were a regular variable, int a and int b, and a had a value of 10, and then I set b equal to a, the value 10 up here would be copied to the value over here. In other words, there would be two values of 10 here. 10 over here with a, 10 over here with b. That's because a and b are completely different variables. But what am I doing on line 12? I'm making a pointer point to something. I'm making the pointer b point to a. So what does it look like? B and A are pointing to the same array. When I change the first element in the B array on line 13, I'm changing it to 42. What do you think is going to happen to A? If I change this thing to 42, and then I eventually print out the first thing in A, what is it going to print out? It's going to print out 42. Right? And you can see that up here when I printed out A. Why? Because I had two pointers pointing to the same thing. So if I change the array with respect to one, the other one sees it, right? Because they're sharing the same chunk of memory. Okay? This is what's known as a shallow copy. Right? Let me edit this code and cut and paste it for you over here. A shallow copy of an array only makes a pointer point to the same array. Right? And here's the example that I just showed you. Okay? That's not what we want. We want what's called a deep copy, which is the antonym of shallow, right? Shallow or deep, right? What we want is a deep copy. A deep copy is a brand new memory location, a brand new separate memory location containing these same elements. Right? So let me go ahead and go back over here. And this is a shallow copy. Let me go ahead and change it so that let's do the exercise that I was just mentioning. What we're going to do is we're going to write a function to create a copy of an array, but a deep copy, not a shallow copy. Okay? So help me out with that here. What should I call it first of all? Oh, copy is both a verb and a noun, so I like that. Right? Copy, or you could really make a descriptive copy of an integer array. Right? If you're not into brevity, all right, and not into the whole brevity thing, right? As the dude would say. Right? So copy or copy of. Right? Copy of is also common. All right, so it takes let me go ahead and write the documentation for you. This function takes an integer array of size n and returns a new deep copy of it. Right? That's what we're going to do. Here's an array filled with 10, 20, 30, 40, 50, whatever. I want you to create another completely brand new array over here, 10, 20, 30, 40, 50, same contents, and give me this new copy. So what am I going to be taking as input here? An array, and the way that I do that is int star arr. Right? Anything else? I have to do the size. I have to do my own bookkeeping. And I already said that the size was n, so I'll go ahead and go with n. Now before I continue, are you going to be making changes to that array? Here's an array. Make a copy of it for me. Copy. Delete everything. Did I say also delete everything over here? No. So let's go ahead and make that as an advertised promise that we're not going to be changing it. Now, if I'm going to return an array, what kind of element should I return? Just a regular old integer, one value? Well, it is going to be one value in the end, one memory address value, though. So, int star. Okay? Now, to actually write this, what I need to do is I need to create a new array. For that, I will go ahead and cut. I don't want you to get into that habit. I'm just doing this for brevity here. Don't copy pasta, right? So I'm going to go ahead and call this copy of array of size n, and we know that it's an integer array, so size of int. And I'll eventually return that copy. Am I done, though? So here's an array of size 5. Create an array of size 5. Did I copy over these 5 elements over here yet? Nope. What do I need to do? I need to iterate over the elements. Int I equals 0. I is less than n, I plus plus. And I'll make the copy, the ith element in copy equal to the ith element in array. There. Now I've got a copy of this. So I'll go ahead and make, instead of making a shallow copy here, I'm going to call my function copy of a, and it's of size n. And then I'll make my change. B sub 0 is equal to 42. And I wish I had not erased that. Undo, undo. Can I do undo? There we go. Yep. And get rid of this. There. Now I'll print out a. Should this print out 42 now? If I have this copy over here and this copy over here, and I change this copy over here to 42, should this copy over here be changed? No. Let's visualize this execution. Hopefully it works. Oh, no. Oh, darn it. I undid too much stuff. There we go. Visualize this execution. You notice I saw that right away, too, because I followed a consistent styling convention. Right? Ignore that. All right, let's go ahead and walk through this. So there's A, and I filled it with 10, 20, 30, 40, 50. I'm going to go ahead and call my function here. The copy of has a reference to the original and creates a completely different deep copy over here. Right? Walk forward. I am copying over the elements. Now I've got 10, 20, 30, 40, 50. I return the copy. And back in main, I've now got A pointing to one copy, B pointing to another deep copy. So when I change the first element over here in B, A is unaffected. And when I print it out, you see the original 10 over here. Right? So this is a difference between a shallow copy, where you're just copying a reference and you've got 2 pointers pointing to the same thing, and a deep copy, where you've got 2 pointers pointing to 2 completely different things, so that changes to one don't affect the other. Right? And that's called a deep copy. Okay? I'll go ahead and cut and paste this as an example over here. There we go. There. Now when I update the notes later on tonight, you'll have copies of that. Okay? The last thing that I want to go over, and we might, oh yeah, go ahead.
Why is there not a simple function already to make a copy? If it's like
Good question.
useful.
That does seem like something useful. And there is. It's called Memcpy. What do you think it stands for? Memory copy, exactly. The problem is there's one function to rule them all. So there's not like an integer array copy function, a double array copy function. It all operates on void pointers. And I tried to limit the amount of void pointers that we have to look at as much as possible. So we only see it in like 3 instances. Yes, if you're in practice, if you're going to copy this thing over here and you just want to do it with one function call, memcpy is the thing that you want. The destination, basically, you have to call malloc first to create memory large enough to do it, and then you have that's your destination. Then you have the thing that you're copying from, copying into. You pass both of those off, and then the number of bytes to copy. So something like this. Let me go ahead and alternatively, I'll put alternatively. What you would have done is B is equal to int star malloc n times size of int. I'm creating the memory. Then I can call memcpy on the destination, the source, and how many bytes do you want to copy? Right there. And so that's what it would look like, right, instead. You have to, it's the number of bytes, not the number of elements. It needs to know the number of bytes because, again, it's a generic void pointer. It doesn't care that these are integers. It doesn't care that these are doubles. It just needs, you want this memory copied over here, that's fine. Right? And then you got to be careful because if you're trying to copy memory onto itself, I think that that's undefined behavior. So if you did something like this, B to B, even though it's valid memory, it might lead to a segmentation fault. Right? And note here, why is the destination first and the source second? What if you were setting int x is equal to 10? You're taking the thing on the right-hand side and moving it into the variable on the left-hand side. And so that's why you're taking this thing and you're copying it into this thing. Go right to left. And that's why all of the standard library functions, if you're copying something into something else, it's right to left. Right? But if you want that in the notes, I'll go ahead and put that here. But if you are interested, RTM, right? Alternatively, this thing right here. But we're not going to expect it at all. But if you want a shortcut, yeah, go ahead. Just learn how to use it properly. Right? All right. Multi-dimensional arrays. Right? So what are dimensions? You can have arrays with more than one dimension. So what do we mean by dimension? What is a 1D array? These are just regular old arrays. Right? Why is it one-dimensional? Well, you've got a line, basically. Here's the first element. Here's the second element. Here's the third element. Just like, what does one dimension look like when you draw it out on a piece of paper? It's just the x-axis, right? It's one dimension. It only goes left or it only goes right. Right? Well, what's two dimensions? Two dimensions has rows and columns, right? You've got the Euclidean plane. You've got x-axis and now y-axis. So you've got two coordinates. X could be 5 and y could be 10, right? And you're looking at the 6th element over here and the 11th element up here, right? And so you can look at it as rows and tables, or rows and columns. In other words, tables, right? Or what's another thing that has both rows and columns? Think mathematics here. Matrices, right? 3D arrays? Yeah, you can do that. Arrays, right? Here you would have rows, columns, and does anybody know what else they're called? The third dimension is called, with respect to rows, columns. Sometimes they're called aisles, right? There we go. It kind of makes sense because if you go down the store, an aisle, you're going deeper into the store. Well, you've also got rows of shelves, and on each shelf has things as columns, right? Here's all the cereal boxes. And there's the Count Chocula, and you've got 5 copies of Count Chocula because they're really trying to push it, right? So you've got aisles, you've got rows, and you've got columns, okay? Aisles, or sometimes they're called, what's the other, or lanes, right? What about 4D arrays? Right? Or do it? What does that look like, by the way? 4D arrays. Yeah, you can't visualize it anymore. Why? Because we're limited three-dimensional beings, right? Instead, how is it usually visualized? And there are plenty of popular movies now that have visualized this. That's the Tesseract, right? From Marvel, what is it called? Infinity Wars or Avengers, that's it. Avengers had the Tesseract, right? Or the other one, Interstellar. He went into the Tesseract because he was time traveling, and that's the fourth dimension somehow. And so he was, it was visualizing 4 dimensions in 3 dimensions. The way that you do that is through a Tesseract. It's just a cube within a cube connected at the corners, right? But there's no way of visualizing this, but you can do it. You can have 4-dimensional vectors. You can have 5-dimensional vectors. You can have 6-dimensional vectors. You can have 4-dimensional, 5-dimensional, 6-dimensional arrays. Don't do it, right? If you are fine, if you, in fact, don't go up to 3 dimensions, right? In general, limit consideration to at most 2 dimensions. Right? If you find you are needing more dimensions, you might instead want a structure. Structures are something that we'll talk about later after the midterm, okay? A structure is something where you can take all of these dimensions. I want 5 dimensions because I've got a first name and a last name and an age and a middle name and a class standing. Great. Take those 5 dimensions and wrap it up into one thing, something that represents a student or a person. And that's what structures are, okay? Usually it's a code smell if you're using 3 or more dimensions, dimensional arrays. But 2-dimensional arrays are perfectly fine because often you have matrices, and you want a matrix, and you want to multiply by another matrix because you want to do a linear transformation. One student in here is contracting to do an extra project where they take a robotic arm and move it through 3-dimensional space. Well, to do that, you need a 3x3 matrix in order to define a linear transform so that the arm can go down like this and over like this and then over like that or something, right? So you do have often you have need of 2-dimensional matrices. In C, a pointer, int star arr, points to a 1-dimensional array. Right? What do you think points to a 2-dimensional array? To point to a 2D array, you need to use int star arr. That's only 1 dimension. How could I add another dimension? Another star. Hey, that looks familiar. Where have we seen star before? Int main, int argc. Then what comes next? Char star. A 2-dimensional array of characters, right? That's an array of strings. Right? And so we've seen this before, and we will look at it again with respect to strings. But for now, we'll just go ahead and limit our attention to integers. What if you wanted a 3-dimensional array? What would it look like? 3 stars, 4 stars, 5 stars. That's why you don't do it, right? Because then you are in your stars everywhere, right? Very, very messy code, right? In fact, an int star arr is a pointer to an array of pointers. Okay? So this is the way that we're actually going to do it. I've got a pointer that's going to point to an array of pointers, and I'm going to visualize it like this vertically. This is a pointer, this is a pointer, this is a pointer, this is a pointer. Each one of those pointers is then going to point to a 1-dimensional array. And if you've got a 1-dimensional array here and the pointer is pointing to it, there's your first row. Here's the second pointer, it's pointing to the second row. Third pointer is pointing to the third row. All right? So I'm going to go with our limited remaining time here. Let's go ahead and write this code. Actually, I'm just going to write this code, cut and paste this code, and then let's visualize it. See what it looks like. Get rid of this. I already have this. I already have this. And let's go with this. There. I want, say, a 3x4 dimensional array. There we go. There we go. There we go. There we go. Oh, this is not my visualizer. Go over here. There. That's better. Visualize this execution. Okay? Now, don't worry about the code. We'll revisit this on Wednesday. But I want to show you what it looks like. So n and m, I'm going to have an n by m array. I'm going to have 3 rows and 1, 2, 3, 4 columns here. The way that it works is matrix is going to point to an array of 3 pointers. And unfortunately, it's not going to visualize it how I wanted, dang it. Well, no, cool. It will do this. It just won't visualize it vertically anymore. There's the first row. There's the second row. There's the third row. Each row was initialized as m times size of int, so it's going to have 4 elements, 3 by 4 elements. So what I need to do, what I can do now after I've created this thing, is I can start setting them. Matrix of I just need to provide two variables. 0, 2 is equal to 42. Which one does that set? Visualize this execution, and I'll run through it really quick. Come on. So step, 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 step. Third, line 13. Which one of these things is going to be set to 42? This is the first dimension. So I go to the pointer and, 0, well, that refers to this array right here. 2, that's the second element? Nope, the third element. So 1, 2, 3. 2 right here, if you can't see it. So this element right here is what's going to end up getting changed, 42. So once you have a two-dimensional array, you've got rows and columns. All you need is two indices to reference the row and then the column. Right? And that's the convention. You go row, that's called row major form. You go with the row and then the column, not the column, then the row. If you want to do something different and go with column major form, that's your business, but you need to do it consistently. Right? We're going to go with row major form. And that's where we'll pick it up tomorrow, or Wednesday, sorry.